Hi everybody, this is Brett, your structural lead for watching Superbike. So today we're going to be doing beam analysis on a motorcycle chassis. And this is a way within ANSYS to do analysis in a much simpler and I guess accurate way. Essentially, instead of meshing all of these solid bodies in ANSYS, you're going to tell it that each of these solid bodies is a beam, basically like something of consistent profile. And ANSYS will be able to take this knowledge and simplify the meshing process by a ton and run an analysis that is a lot faster and presumably a lot more accurate to run because the entire meshing process is just insanely simple. So we're going to start out with this model in Solidworks. This is all done up. Instead of a spring, I just put a weldment here, but that's fine. And we have all this nice 3D modeling stuff, and we will not be able to take that into ANSYS. Unfortunately, ANSYS does not appreciate built-out 3D geometry, built-out solid geometry when taking into analysis with beams. So we're essentially going to have to roll back all of these solid bodies until we're left with just the original 3D sketch. And we're going to want to turn this into a bunch of curves. ANSYS does not accept simply sketches, you need to give it curves. And the way to do this within SolidWorks is to make composite curves. And composite curves also do not like disjoints like this. Like this will not fly within composite curves in ANSYS. So you're essentially going to have to convert the entire model into a bunch of smooth curves within sketches. See, we have a nice smooth one right here. Let me exit sketch. And once that's still selected, so we're going to do curves, composite curve, 3D sketch, and there we go. And if you hide the main chassis here, you'll see that we have a composite curve. And over here, I've already completed this process with another chassis, and we're going to save this as an IGS file. An IGS file is one of the few files that exports to ANSYS curves, and ANSYS will be able to read it. And from now, we're going to move into ANSYS. Alright, so now we're in ANSYS. So we're going to want to first set up this geometry tab. This isn't necessary, but I think it's just a nice step to establish where you are setting up the geometry, because there's a lot of modifications that we're going to have to do to the original IGS file before bringing it into analysis here. So just import that into ANSYS and open it in Spaceclaim. So now we're in Spaceclaim. Unfortunately, you can't see anything. That's just kind of how it goes sometimes with ANSYS. But if you highlight them, you can see that everything's here. So what you're going to want to do is tell Spaceclaim that these are going to become beams. And we do this using this Prepare tab. And this beams section right here will have certain profiles, and we're going to select all of the lines. Profiles, we'll give it this tube profile and tell it to turn into beams. There we go. Now we have a ton of separate beams, except you can't see them. So to fix this, we're just going to save this. We're going to exit out. Then we're just going to reload with that Spaceclaim document that we just saved. Feeding ANSYS back the Spaceclaim document essentially helps it figure out what you're trying to tell it. Because ANSYS and Spaceclaim are kind of built into each other, it just works a lot better. So now that we're able to see everything, you'll notice that this extra piece here, I don't know where it came from. We're just going to go delete that, just hit delete. And we're going to select this piece and also hit delete because we're going to be adding a spring there instead. And now we just have like this nice, fairly cool looking truss frame. But we're going to want to separate it into certain bodies because otherwise ANSYS won't exactly recognize it nicely, and we're going to have some issues when setting up the swing arm to swing on its own. So we're just going to have to go through these and select all the geometries that are part of the swing arm. Okay, so there's the swing arm, nothing more, nothing less. We're going to right click this and move to new component. And we'll rename this one swing arm. And for the rest of these, new component, frame. Now you'll notice here that I'm using the same profile for all of the beams. That's probably not what you're going to want to do when you're running actual analysis, but for the purposes of this video, it'll suffice. And you can just change this by changing the profile down here, making sure you already have another one set up. So now that this is done, save it. And we'll go back into ANSYS Workbench. Okay, so first thing we're going to want to do is a static structural simulation. So we'll do this and drag it here to ensure that the geometry is shared. We'll drop into engineering data. And structural steel probably will work. We can also go to the data sources, the ground to library, and just select another material. Well, let's do stainless steel. Okay, now that that's done, I'll go into the model. Awesome. So now we're in ANSYS Mechanical, where we will run our analysis. So, looking at this, we have the entire chassis over here, and we're going to want to begin setting it up. So one thing that we'll have is a spring, and this is built into ANSYS. We can go here, insert spring, and we'll just select the reference. We're going to want to switch cursor mode to vertex here. Select right here, and select our mobile as right here. You'll notice that there are vertices here, and this is because within Solidworks, I split up these into two pieces to ensure that there would always be a vertex here. And you're going to want to do the same at any point where you think you're going to be applying any sort of load or fixed geometry. If you want that point to be a point of application, you're going to need to separate everything around it so there is a built-in vertex. And we'll just give this 110,000 newtons per meter because that's, I think, the spring constant we're going to be working with. Now, we're also going to do connections, insert, joint. And because this is a swing arm, it'll pivot around this beam right here. So we're going to want to make sure that ANSYS knows that this is what it's supposed to do. So I'm going to cursor mode, edge, and hide these segments. And you can access this menu by right-clicking on the screen. So for this one, I'll go cursor mode, vertex, select this edge over here, make it my reference, and I'll insert another one, and make this my reference for the other one. And we're going to here just invert visibility to show joints. So we're going to go over here, do the vertex, mobile, and mobile here as well. Sweet. Now that this is done, we're going to want to show all bodies. And since this is a swing arm, it needs to rotate. And this joint registers at fixed, which is not rotational. So we're going to switch it to revolute. And what you'll notice is that revolute only allows revolution within around the z-axis. So we're going to want to expand this one and go to the reference coordinate system. And the principal axis is z, so we're just going to want to define that by the x-axis and do it to this one as well. And then the z-axis is in line with the rotation that the swing arm should be undergoing. Okay, now we're going to want to set up our boundary conditions. So we'll just apply a fixed load here at the head tube. Oop. Cursor mode edge, head tube, fixed support. And we'll just apply a line pressure here to kind of represent the wheel pushing up on the axle. And this will be, we'll give it the full acceleration load. So look at the axes, Y over there. And when you're defining by components, you just do 1500 and Y. And you get an arrow pointing upwards. And Z, we're going to want to be propelling it forward. So it'll just give it negative 500 newtons. And there we go. There are our boundary conditions. And for solution, insert deformation total. And we're going to want to insert beam results. Oh, sorry, beam tool. And here is where the beam analysis in ANSYS really shines. Because if you were analyzing that other model, the original one, it would have to mesh all those pipes within ANSYS, and it would just have this really weird looking geometry. But here, if we just tell it 0.01, that's our element length, it'll chop up every beam into pieces of 1 centimeter each. And it looks pretty good. Since this is a beam, each element is like, ANSYS knows exactly what it is. It doesn't need to chop it up into smaller pieces with weird geometries to figure out that it's a beam, because it already knows. And that's the real strong suit of this type of analysis. So now that the mesh is done, we'll just solve it. Okay. So we have an error here. ROTX to view freedom, go to object. Hydraulic bodies. Okay. Something weird is happening with this one. And only that one. So to kind of diagnose these errors, one way is to do modal analysis. Okay, now that we're back into mechanical, we'll just do solution, deformation, and solve this modal analysis to see what happens when you vibrate the frame. Because this simulation typically works even if something isn't quite right, as far as I've seen. And it'll kind of show us something. Okay, tubular, yeah, fine. Show all bodies. Okay, so there is something quite wrong here. One of our pieces has flown off of the frame. That's not good. We have 1.2 meters of deformation. Very much not good. So we're going to want to go back. And I happen to know what the error is. I kind of did it on purpose. We're going to want to go back in geometry. So now we're back in Spaceclaim. The thing that I didn't do is merge the topology, which is something very important. It essentially tells ANSYS that these are like a coherent body. It's not just a collection of random things that aren't connected. Now that this is merged, some things will change. So now we are back in mechanical. And if you click on geometry, you'll see that it's now separated into two pieces, swing arm and frame, which is what should have been done originally. And all the connections will need to be reset. So let's see. We'll reset the reference here. And our spring should be good. Joints 1 and 2. Okay. Static structural and line pressure. Just need to reselect that. Apply and solve. So you'll notice that an error flashed that I was doing this with large deflection turned off, and that's definitely something that I will address. Not before showing you the results here. 0.001 that is not a lot of movement, which is odd because this is a swing arm, which its purpose is to move. And also, if you look at the stress here, it's not symmetrical about like the middle of the bike, which tells me that something is off with the analysis. So the first thing, I'll go analysis settings, large deflection, turn that on. And the only thing really that would be possibly asymmetric is the connections. Now I flashed it up on the screen earlier, but I ignored it because I wanted to show it what happens, but one of these got switched back to a fixed joint. So we're gonna want to switch that back to revolute. Make sure that the axes are all still correct. Those look good. And we're gonna want to solve this again. Okay, and now 4 centimeters. That makes a lot more sense. Stress, all symmetric across the middle of the bike. Find the stress, symmetric. That makes sense. There's stress here where the spring connects and stress over here. This overall, the analysis makes sense now. And if you look at this, get a cool animation of the swing arm moving. There we go. That's how you run a beam analysis on a motorcycle frame. And just to recap, the beam analysis is much better than the original one, at least in terms of speed and most likely accuracy, because of this mesh. Just to illustrate my point on the meshes, we'll be taking a look at the old mesh for the old frame compared to the mesh for this current frame. As you can see, the mesh for this frame with the beam analysis is all nice and symmetric. It looks really nice. Nothing's crazy. And when you go to do mesh quality, there is none because ANSYS knows that it's a beam. It doesn't have to do any guessing, which is essentially what meshing is. And if you compared that to this old frame, there's a large difference. This old frame was imported as solid geometry, and such it had to mesh. ANSYS tried its best, and so did our old members. However, it's hard to beat ANSYS when ANSYS knows exactly what it's supposed to do. And if you check on element quality, which is essentially like a measure of how mostly like symmetric your elements are, your goal is to get close to 1, if at all possible. We are at 0.01. That is not good. As far as I know, I would try to run above 0.25 at least for analysis, and this is far below that, and a subpar mesh will result in errors. So this is not good and definitely should be addressed. And this frame could mostly be boiled down to a bunch of beams. There's some things here that you will need to probably run separate analysis on just to make sure that they all work, but for the most part, this frame could be turned into a series of beams. And that would give you a much nicer mesh like this, a much more smooth running calculation, and most likely a more reliable one. Because while this may not factor in all the details in the exact model that this one has, such as like this component right here, that penetration, this will have a much cleaner mesh that results in a much more accurate running ANSYS that will reduce those random errors that tend to come up when you have a not so great mesh. And I hope this video helps you on your ANSYS journey. Just analyzing frames in this manner is much better of a way, I believe, and it makes for a much more powerful calculation. And I hope this video really helps you in your next foray into chassis analysis with ANSYS. Thank you.